Hi, everyone. Today, I'm going to talk about this prediction called YJIT makes Rails 1.7 times faster. And I need to apologize. This was a lie. As of this morning, it's like 1.8 times faster. So my name is Kokubun. I work for Shopify on the Ruby infrastructure team. Shopify has Ruby and Rails infra team that Ufuk explained in the previous session as 35 people team. And under that team, we have Rails infra team, Ruby infra team, and Ruby DX team. And I'm in the Ruby infra team, which consists of those people. And there are teams, like sub-teams like this. YJIT team has 5 people, and I'm going to talk about the YJIT thing. So YJIT is a JIT compiler. JIT stands for just-in-time compiler. And the purpose of this talk is to make you feel like you need to use this in production. Also, you should feel that you need to upgrade Ruby version to 3.3, the latest version. So what it does is when YJIT is enabled, it's, by the way, disabled by default, so you need to turn on explicitly. And if you enable YJIT, and if you call some methods more than 30 times, it triggers the JIT compilation, and JIT compilation converts that method to native code. And from that method, the methods called from that entry point will also be compiled in the YJIT design. And in production, we are using YJIT for the most important services. One of that is Shopify storefront renderer. And that's speed up. The speed up is like 17% faster in production. Like this service has the largest traffic in our company, like billions of traffic. And so this is like battle-tested JIT compiler. And I went to a lot of booths in the RubyKaigi sponsor booth, and a lot of people talk to me like saying, we are using YJIT, and thank you for using YJIT. I'm also wondering, how many of you are currently enabling YJIT in production? Could you raise your hands? Oh, yeah, right. So yeah, I want to make everybody raise your hand next year, so please do, yeah. So to do that, enabling YJIT has several ways. The most basic one is the --YJIT option to the Ruby command. And in addition to the Ruby opt environment variable that's available by default in the Ruby command, there's also a special environment variable specific to YJIT, which is Ruby_YJIT_enable and 1. If you pass this environment variable, YJIT is also turned on by that configuration. And finally, from Ruby 3.3, we have Ruby VM YJIT enable, which could be called from the Ruby script without even passing any configuration to Ruby beforehand. And the good news is Rails 7.2 is going to include the default initializer that enables or calls this Ruby VM YJIT enable method when it's available, like for 3.3. So as long as you upgrade Ruby and Rails to 3.3 and 7.2, once it's released, it's going to generate such an initializer when you call that Rails new. So YJIT effectively becomes the default JIT compiler in production. So please use it when you upgrade Rails to 7.2, or you can also use this as long as you upgrade the Ruby to 3.3, sorry. And then I guess one of the challenges in enabling YJIT in production is the memory usage. So there's always a trade-off. Getting performance could mean that you might need to use more memory, so that could be used for optimizing your Ruby execution. So one of the tricks we are currently kind of recommending to the community is to tweak the parameters called YJIT exec mem size. So this controls the number of bytes that are allocated for JIT code. And by default, it's 48 MIB from 331. As of 330, that was 64. But the purpose of this default is meant for maximizing the speed. Like for most large applications, even for Shopify's largest monolith, that's kind of like 48 seems sufficient. So if you run like a monolith repository, I think it's also sufficient, and then it guarantees the speed. But I think in many deployments, you may want to kind of reduce the amount of memory used for your service instead of maximizing the speed. So in that case, you could try 32, 24, or 16. I heard that GitHub folks are using a smaller memory configuration. So I think as long as your application is like more like smaller than GitHub, you should be able to do that too. And the caveat here is exec mem size only controls the JIT code size. So YJIT also needs to maintain the metadata for each JIT code. So if you configure exec mem size to, for example, 32, it could also use metadata memory like 64 or like 96. So that's also like controlled by this configuration currently, kind of. So if you limit the number of configurations, that also like, automatically reduces the metadata as well. So you could use this to control the YJIT memory usage. And we go over this kind of tips for production deployments in the Ruby's doc YJIT.YJIT-MD. So please check it out to deploy YJIT in production. So the next part, the second part is going to be about what kind of YJIT 3.3, Ruby 3.3 improvements we made in the latest version, so that I want you to understand why YJIT is getting faster over like version upgrades, and I want you to use the latest version and kind of want to convince you to use that in production. So out of a lot of features that we released in 3.3, there was one single change that improved the Rails performance, Rails bench performance by 7%. By the way, there was a discussion of 5% improvement in string reader, but that was like 5% is a lot if you ever worked on performance optimization. 5% is very significant, by the way, and 7% is even more significant. So that's a quite significant improvement. So if you look at the list of the YJIT changes 3.3, can you guess which one was the most like significant in terms of the Rails performance? What? What? Oh, yes. So the Virut is saying, so he added the blank method, blank or present method, specialization to Rails 7.2, and then YJIT improves the performance by inlining that method, but unfortunately that was not the case. So this is the most significant one, and this is pretty hard to understand, so I think I wanted to take this opportunity to explain why this was significantly influencing the performance. So I'm calling this method called fallbacks. So if you look at this code, this is pretty normal Ruby method, so there's no problem compiling everything in this method. So in the Ruby virtual machine, we compile Ruby source code into so-called reverb instructions. It's internally called instruction sequence. And these are, you don't need to understand the sequences, but I just wanted to show kind of like a pseudocode to explain what is happening behind the scenes. So the right side is completely made up pseudocode, which is, so I wanted to just say, each instruction is optimized by JIT as long as we successfully compile each instruction. So in this case, there's like everything in this code is supported by YJIT for specialization. So in this case, the ratio in YJIT is like 100%. However, some of the types of, some types of the Ruby code is not supported by YJIT. I mean, YJIT is not capable of optimizing some patterns of the Ruby method calls. One of that was keyword but I forgot, sorry, keyword rest, or yeah, sorry, keyword rest, but sorry, this was not the keyword rest. But anyway, so assume that this is not supported by the YJIT you're currently running. And in this case, the instruction in the Ruby Brim instruction is something that YJIT does not support. And in such situations, we used to generate a side exit. So side exit means you need to exit the JIT code and then go back to the interpreter execution. In that case, you need to go through the interpreter loop to execute the Ruby Brim instructions. So which is obviously like slow than executing the machine code specialized for Ruby method, this particular Ruby method. So in this case, we kind of call it ratio in YJ like 33%, and this is pretty low. We are able to compile everything else, like other than the bar method call, like dupe instruction and set ivar stands for instance variable, and leave is just a return from the method. All of these, like the 3 instructions following the method call is supported, but because of the side exit in the middle of the method, we ended up not compiling the instructions followed by the unsupported method call. However, what I did is kind of taking the idea of mjit. So mjit is the JIT compiler that was merged in Ruby 2.6, and I removed it in the 3.3, which used the C function called vmsend. Precisely, it's actually called vmsendish, but send instruction has its own interpreted implementation, which is implemented in C code. So we could call back the C function that implements the send method call logic for interpreter. So what we did in the 3.3 was to just call back the interpreted information. So if you go back to the previous slide, this is like the send instruction was executed in the interpreter. So you might wonder what is changed by calling back the interpreted implementation. So if you call the virtual machines method call implementation here, what happens is after that instruction, there's like a instruction that could be optimized by YJIT. So because we no longer exit this JIT code in this method, the instructions followed by this method call can be also optimized. So now ratio in YJIT becomes 100%, like from 33%. So like it's a lot of more like optimizations in the single method. So if you accumulate this kind of changes over the whole application, usually in Ruby 3.2, in our production applications, the ratio in YJIT was something like 90%. So like 10% of the Ruby virtual machine instructions were not JIT compiled because of this constraint. But when I upgraded the Ruby version from 3.2 to 3.3, that improved like to 99%. So almost all instructions are now JIT compiled because of like this kind of improvements. So please upgrade your Ruby to 3.3, which is the main takeaway from this presentation. This is kind of like a summary. So this was the explanation for the unsupported codes, but the other case is the megamorphic codes. So this is kind of like a compiler terminology, so I'm going to also explain what is the megamorphic codes. So this is one very small example of the megamorphic dispatch. So megamorphic is like a more significant version of the polymorphic dispatch. You might have heard of the polymorphic or polymorphism. The mega is just a more poly version of polymorphic. And so in this case, this is just a single inheritance. So the method called X is going to call this XA in the A class. But if there are more subclasses of the X, there could be more dispatch targets from the call method in the X class. So in this case, what YJIT generates as of Ruby 3.2 is that in the call method, when it calls X, we check the self class, and then if self class is A, then just return the symbol A for the A's explanation, and then we kind of follow the same pattern, and then just add the branches to this X method call. So by the way, this is something the interpreter doesn't do. YJIT has the so-called polymorphic inline cache. So interpreter has only a single entry in the inline cache. So let's say when your program calls A's X and B's X interchangeably, then you're gonna make a method search from whenever you switch the class of the receiver in the XX, and then YJIT, on the other hand, is able to cache multiple entries in a single method call. So we are going to support, we can support like A, B, C's X in the same place by making this kind of branch. However, if you append this kind of chains forever, then that's gonna cause a lot of overhead for just checking the class. So what we do is there's some limit in the number of chains, and we then append a side exit at the end of the chain. So this is the Ruby 3.2's behavior. As I explained before, if you make a side exit, then you're not gonna be able to execute or JIT compile the subsequent instructions. In this case, after coding X, there's the instruction variable set X equal. So setting the instruction variable is not JIT compile in this case. But we made the improvement, again, using the virtual machine send implementation. So 3.3 YJIT can avoid stopping the compilation there, and then just JIT compile the subsequent instructions. So that way, the ratio in YJIT is maximized to like 99% because of those improvements in the 3.3. The next topic is exception handlers. And if you hear exceptions, you might wonder, is this only about the raise method? The answer is no. Internally in the Ruby virtual machine, exceptions are used a lot in many other places other than just a raise method call. So if you look at this example, there's a break in the array each method call. And break seems like a pretty safe operation in a block. However, internally in the Ruby virtual machine, it's called throw tag break instruction. So it does throw exception in the Ruby virtual machine world, and then it's handled by the catch table to handle the exceptions, like internal exceptions. So I'm going to just go through how it works. So when you enter the foo method, it pushes the call frame foo to the stack, and then it also calls the array each on the array each method call. And then after that, array each calls back the block given to array each, and it starts executing the block. Then what happens is when it reaches the break statement, it needs to pop multiple frames. So this is why we need to implement it as an exception. So because array each by default returns the receiver, which is the array, but if you use the break statement, you can return something else from the array each. For that reason, you need to pop the array each first, and then pushes the some like argument given to break, which is a local variable in this case. So we kind of need to pop the multiple frames here, which is why we use the exception. And after that, because in Ruby 3.2, because we didn't support exception, compiling exception handlers, we need to execute the subsequent code, like setting the instruction variable foo in the interpreter. So that way, if you run Ruby 3.2, this is going to be ratio in YJIT like 60%. But in 3.3, because we supported the exception handler method calls, we now make it ratio in YJIT 100%. So 3.3 is like YJIT that can compile everything for you. So there's a trade-off, by the way. If you upgrade from Ruby 3.2 to 3.3, obviously, it's going to be faster, but it compiles more code. So in that case, that might consume more memory for that reason. But you can still use the exec mem size configuration to limit that. And from our experience, reducing that doesn't do reduce a lot of performance. So you could just use that and then kind of maximize the performance in the hotspot. The next topic is a new register allocator for stack values. Ruby virtual machine is implemented as a stack virtual machine. So it internally maintains its own virtual machine stack. And we implemented a new register allocator for those values. So I'm just going to go through how it works. So as of 3.2, if you have this kind of 1+2 method call, the instruction looks like this. And there's a put object instruction that pushes just object 1 to the stack, then pushes 2, and then if you reach the pass instruction, it pushes pops 2 objects and then writes the result 3 to the memory. What I wanted to say here is that it's only working on the memory. Every operation goes to memory, and your computers have both registers and memory, and registers are closer to the CPU. So writing to registers are faster than writing to memory, basically. So 3.3 is going to write to register 1, as if it was the first slot of the stack. And then the 2 is going to be written in another register, as if it was the second slot of the stack. And then the pass instruction is going to write to the first register, as if it was the first slot of the stack. And then it's going to just work like that. And there's a lot of complications we needed to handle, but basically this is how Ruby 3.3 YJ optimizes your operations. So this applies to almost every instructions in Ruby virtual machine. So Ruby 3.3 YJ should be able to optimize your code across the board. So please upgrade Ruby to 3.3. Another complexity is that we also want to expand this register allocator to local variable. So this is not available in 3.3, but we already merged some improvements to 3.4. So you might know that there is a feature called kernel binding in Ruby, which allows you to manipulate the local variables in the current frame. So if you allocate this kind of binding object, what Ruby virtual machine does is escapes the so-called environment of the local variables from the stack to heap. And if that happens, any method can modify the local variable of the current frame. So it's kind of dangerous if you just allocate registers for the current frame that way. So to deal with it, we introduced the optimization, the hook to kind of correct the current state when methods like kernel binding and also methods like proc new, which also capture the environment, is called. So by doing so, we now have the foundation to allocate registers for the local variables. So hopefully, you will see the performance improvements in the local variable access in Ruby 3.4. So please keep upgrading the Ruby version to the latest to get the full of the performance in the CRuby. Another topic is method inlining for Ruby. So there was also improvement in the Rails recently. Rails 7.2 had patch by root that adds the specialization for the present method. So if you don't know the present method, you can, there's a Ruby a built-in method called .neo question. Similar to that, blank question works like new question, but it also returns true for something like empty string and empty arrays. And the opposite of the blank is the present. So the present information used to be something like exclamation mark blank, but the problem is the blank method is implemented in so many types of classes. So by roots added a specialization for present by replacing the exclamation blank to something just something like false or true. So now the implementation of the blank, present, is kind of something that YJ can easily optimize. So on top of that, we added the inlining implementation for that kind of methods. So Ruby 3.3 can inline single-line methods that return the immediate values like integers, true, false, new, and some static symbols. 3.4 also added support for just self or local variables. In this case, it's going to be argument. This is the the active supports blank and present implementation. It used to be this bunch of instructions in 3.3.2, but now it's just a single move instruction. So it's a lot faster. This also applies to the some built-in class methods like symbol2sim. So this just returns a self from the symbol. So like symbol2sim is also like symbol, so nothing needs to be done. So just return self. And this is because self is optimized in 3.4, it's not going to be optimized in 3.3. But if you look at this code, this is implemented in Ruby, and we are rewriting C method implementations in CRuby to Ruby to automatically unblock this kind of optimization. So you should be able to see more Ruby code in the CRuby implementation instead of the C method. So it improves your productivity if you contribute to the CRuby, and also like it's easier to read. And makes YJIT faster. So Ruby is good. Like writing Ruby is often faster than writing C in CRuby world. So please write Ruby. And another example is Solve helper patch. So like Solve is a type checker, and we use Shopify, and it by default does a bunch of checks given to such helpers, but in production, we don't need to run the type checks because that's already verified in CI. So we monkey patch those methods with an empty implementation, like just return the argument given that was being checked by the type checker to just make it a return value. So those are just a local variable, and these kind of patterns are also inlined by the Ruby 3.4 YJIT. So if you upgrade Ruby to 3.4, then there's also going to be just a single instruction instead of just a whole bunch of instructions like this. Finally, I'm also going to mention the method inlining for C. So C code is kind of like a black box for YJIT, so we can't easily optimize those method codes. However, there are like several method codes that are very popular in many real-world applications. So we kind of target such popular methods and then try to maximize the ratio of the inlining by tackling those popular methods. And there are like a bunch of specializations that we made over years. So like we kind of duplicate those methods by writing this kind of assembly code for every single specialized method. This is a lot of work, but we have like 5 people in our team, so don't worry about the maintenance. And one improvement in 3.3.4 is that there's this function like helper called gprepare lazy frame. So one of the challenges in inlining Ruby methods is that if you inline Ruby methods, that might do something that's kind of difficult to handle. For example, exceptions. So when the method takes argument, it usually could also raise arguments, exceptions like argument error. In that case, we need to kind of deal with the situation. Like if something is raised from the JIT code, that could go wrong in many ways. So for example, if you inline string set by implementation method, which is implemented by this function, you are not going to push the frame when you call this assembly. But if you raise the exception should have the frame for the set by in the backtrace. So what we do is when it raises, we insert the hook in the Rails raise implementation, and then just lazy push the frame for the set by looking at the program counter, which is actually maintained by this assembly code. So like we only set the program counter, and then it's going to be lazy converted to a frame when something is raised in the C function called inside this specialization code. The conclusion is please enable YJIT in production. And we kind of have observed 10 to 20% improvements in production. And also, please upgrade Ruby to 3.3. And if possible, please also upgrade Rails to the latest version. When it's 7.2 is released, it's going to also help your application's performance too. That's all. Thank you.